The distributive law. Now settle in for a bit of a long video here. The proofs alone for this law take longer than being forced to watch the Star Wars prequels. However, it is likely that watching me explain simplification laws using truth tables might be marginally more entertaining than watching The Phantom Menace at least. There are two versions of this, but we'll start with this one as it's the one most commonly applied in exam questions. Yes, I'm nothing if not pragmatic. The distributive law states that A and B or C, in brackets, can be expanded to become A and B or A and C. Likewise, if we go back the other way, we can essentially remove the common factor of A from the chunks to turn it back into the bracketed version. For those of you watching that have a knowledge of mathematics, this is very much like multiplying out brackets for the left to right conversion and then factorisation of common terms for the right to left version. And in fact, I will be using those terms as we discuss them. The circuit diagram for this expression is cool. So we're really saying that we can build this same output using 2 or 3 gates. Now one is going to be significantly cheaper than the other, that's for sure. Let's take a look at the truth table and, oh, that's a bit on the epic side, isn't it? We've got 3 potential inputs, so that's every combination of A, B and C that can be achieved. In fact, this is the exact sort of truth table that we've worked on in the combining gates video. Now this would be an ideal point to work through it yourself for revision. Pause the video and give it a go. If you've done it right, then you'll find that the A and B or C columns and the A and B or A and C columns should have exactly the same value. Right, let's see how you did. And for those of you that just ignored me and want to see the results, buckle up for me. I'm just going to be saying ones and zeros for quite a while. Our first column is for B or C. We can hide the rest of it because we don't need anything other than B or C, and we're looking for either B or C or both of them having a 1 in the box for us to pop a 1 in our answers. Let's whip through them. Both zeros means a 0 output, and that's the same again. Another 0 output. Aha, there's a 1 here, which gives us a 1 output. Another 1, and again, and again. Here we have both values set to 1. Now with an OR gate, that still gives us a 1 as an output, and the same again at the end. On to the next column. To work this one out, we need both the A columns and the B or C column to be 1 in order for us to get a 1 as the output. Otherwise, we'll pop down a 0. 2 zeros here means a 0 output. Just a single 1, so a 0 again. Another single 1, giving us a 0, and aha, a pair of 1s. Both inputs being 1 in an AND gate gives us a 1. Another single 1, meaning a 0. A pair of 1s, meaning a 1. A last single 1 giving a 0, and a final pair eliciting a final 1. A and B requires both values in the A and B columns to be 1 to get a 1 as an output. The first row is all zeros, so it's a 0 output. A single 1 here and here, but oh, 2 1s on this line, giving us our first output of 1 for this column. 2 zeros again, single 1s, and another single 1, all giving us a 0 output. But we finish on a pair of 1s, giving us a 1 output. A and C requires both A and C to be 1 to output 1. Nothing for the first row, or the second, or the third, or the fourth, or the fifth. It's not until we get to the 6th line that we've got a pair of 1s. See, you do get something for a pair in this game, and that's a 1 output. Another 0 here, but finally, another 1. Lastly, we're going to use both these columns with an OR. Remember, if there's a 1 in either column, then we'll get a 1 as an output. And if the law is true, then this column should be a repeat of A and B or C. No 1s here, or here, or here. Aha, a lone 1 means a 1 output. Nothing here, another 1, and another nothing, and finally, the double 1 gives us a 1 output. Let's compare those columns then. Well, the proof's all there. These two expressions mean the exact same thing. So that means that we can move between them. Let's take a quick look then at how we can actually apply that rule in practice. We'll start here and apply the chunking method to group our AND chains and our OR groups. So it looks to me like each of these AND expressions contain a common factor. They've all got an A in them. In fact, they've got an A and in them. Let's see if we can factorize that out then. Since we're removing an AND A, let's set up the brackets. I'm popping A and outside of the brackets, and now let's go through each of the yellow expressions to see what's left if we remove A and from them. If we remove A and from A and C, we're left with C. Let's move down the OR. A and from A and B leaves us with a B. Again, take down the OR. And finally, if we remove the A and from A and D, we're left with a D. And that's it. We've applied the distributive law to the expression and factorized out the common term. Now, in a real world question, there would be further steps that would suddenly become visible at this point, but not in this very simple example. Another one to take a look at, A and C, or B and C, or C. Now let's chunk it so we can see what the expressions are, and straight away we can see that all the expressions contain a C. Let's see if we can factorize that out. So once again, let's set up our brackets and pull out the AND C that we're taking out as the common term. Now, AND C away from A and C gives us A. Copy down the OR symbol. On B and C we end up with just B. Again, copy the OR and hold on a second. Just how do we factorize out an AND C from just a C? What does it even become? In order to remove an AND C from a C, we needed little help from some of the other rules we've learned along the way. A few videos ago we met the identity law, which described a simplification from A and 1 to A. So, if we factorize AND C from A, then we'd be left with a 1, as they mean the same thing. If you're not too sure about this, then just take it as a rule that AND C being factorized out of C leaves us with just a 1. This means that we end up with a 1 in the bracket. Hold on, this is a good thing. The moment we get an expression that has a 1, there's bound to be some more simplification we can do. Lo and behold, anything or 1 is part of the annulment law, where anything or 1 can be simplified to just a 1. This means that the chunk of ORs in the bracket becomes 1. We're left with C and 1. Hold on, that's another law, isn't it? Yes, the identity law again. A and 1 is A. So, in our expression C and 1, we're left with just C. Now, that's pretty impressive that we've gone from a huge expression to just one term simply by starting with the distributive law and working from there. In this example, we're going the other way, expanding the brackets this time. So, D and A or B or C in brackets. What we need to do here is to take each term in the brackets and see what the combination of the left and right side becomes. We'll start with A, so D and A becomes, you've guessed it, D and A. We'll bring down the ORs just as they are and move on to the next symbol. That's a B, so we get D and B. Another OR to bring down, and finally the C gives us D and C. Not too shabby, really. Now, the distributive law also applies to the other combination of gates, where A or B and C in brackets is the same as A or B and A or C. Notice how the brackets affects the way in which that's interpreted, as we do the brackets first. Circuit diagram wise, we're looking at the difference between a 2 and a 3 gate arrangement again, but either way, being able to move between these expressions will involve expansion of brackets or factorization. Proving it in a truth table is another great opportunity for you to practice your combining gates skills. Give the video a pause and work it out if you can. Remember, the values of A, B and C are just all the potential values that can be set by controlling these inputs. And if you've worked it out correctly and the law is true, then the columns A or B and C, as well as A or B and A or C, should have identical outputs. All done? I can see my analytics, who actually pauses the videos, mind you. Let me tell you, lots of people must be enjoying me talk ones and zeros too much to possibly pause it as the data suggests it's less than 1% of you who actually pause and attempt the questions. Anyway, let's go through it. Starting with B and C. So let's hide the columns we don't need. Remember, if you need to do this in an exam situation, then I'd really suggest that you do hide them, maybe with your hand or a piece of paper, as it's very easy to go wrong when you're constantly writing ones and zeros. So, B and C gives a 1 when both B and C are 1. Anything else is going to produce a 0. Starting at the top, we have 2 zeros, so a 0 output. Another 0 output, and another, nope, finally, 2 1s, and again on the bottom row. The next column is an OR, so if we see any 1s in the row, we get a 1 as an output. Otherwise, it's 0. We start off with a 0, then a 1, as there's a 1 in the input, then a 0, a 1, a 0, a 1, another 1, and again another 1. A or B next. We're looking for either of these columns to contain a 1 to get a 1. Not so for the first row, 2 zeros. But a bit of luck here, so 1, then again, and again. Back to a 0 for this one, but then we get a 1, 1, and a 1. Fantastic. A or C. Again, either value should be a 1 to get a 1. We're starting with 0, then 1, 0, 1, then 1s all the way to the bottom. Final column now. This is the AND of the 2 columns shown. We need 1s in both columns to get a 1. So, sad times here. Just a 0, then a 1, a 0 again, a 1, a 0, and then a bunch of 1s. Do those columns match then? Well, of course they do, otherwise there'd be little point in me trying to teach it to you. This law is proved, and we can have a go at using the rule in action. It's worth pointing out at this stage that you rarely see this version of the distributive law in the exam question. Now this is because moving from one to the other requires bracketing, and this massively reduces the opportunity for further simplification, like we saw in the previous set of examples. We're starting with A or C and A or B and A or D. Chunking is a little different here, as the bracket connects the ORs together in their own little sections. But hopefully you'd see from this that there is a common term, it's the A. And we can try and factorize that out. We're actually removing the A OR as the common term, so let's set that up in the brackets and bring down the A OR to the left-hand side of the expression. Now, we repeat the process we've done before for factorization. If we take A OR out of A or C, what are we left with? It's a C. So that comes down into the brackets. The AND follows along, then we're left with a B here, the AND follows down, and finally we end up with a D. A final expression of A or C and B and D is as far as we can go with this one. As I said, this second version is really employed as it doesn't lend itself to simplification as well. But there's nearly always some distributive law that needs to be done, whether that's factorizing out common terms or multiplying out the brackets. It's just commonly done with the AND version rather than the OR version. The examples we'll look at in the past paper questions will mostly have that in common, particularly at A level. That's it for this video. Don't forget to like, comment and subscribe to get more computer science content.